Picture this. Right now, as you watch this video, there's a world orbiting a distant star, a world that might harbor life, a world that could become humanity's second home. It's so close in cosmic terms that we can almost touch it, yet it remains impossibly, maddeningly out of reach. Welcome to BrightBoundX, where we explore the frontiers of human ambition. Today, we're diving into one of the greatest challenges our species has ever faced: reaching Proxima Centauri, our nearest stellar neighbor, and why this 4.24 light-year journey represents the ultimate test of human ingenuity. Proxima Centauri isn't just another pinprick of light in our night sky. This red dwarf star, barely visible to the naked eye, has captured the imagination of scientists and dreamers alike for one extraordinary reason. It hosts Proxima b, an exoplanet that exists within the habitable zone, that precious Goldilocks region where liquid water could exist on a planet's surface. Think about the magnitude of this discovery. Among the hundreds of billions of stars in our galaxy, the closest one to us happens to have a potentially habitable world. The odds seem almost too convenient, as if the universe itself is extending an invitation. Proxima b is roughly 1.3 times Earth's mass, and orbits its star every 11.2 days. But here's where it gets fascinating. Because Proxima Centauri is a cool red dwarf, much dimmer than our Sun, the habitable zone exists much closer to the star. This proximity raises tantalizing questions about tidal locking, atmospheric retention, and the star's infamous stellar flares that could strip away any atmosphere. Recent observations suggest there might be additional planets in the system Proxima c, and possibly others. We're not just looking at a single world, we're looking at an entire planetary system that could teach us profound lessons about planetary formation, stellar evolution, and perhaps most thrilling of all, the conditions necessary for life to emerge. The stakes couldn't be higher. This isn't merely academic curiosity, it's about securing humanity's future among the stars. Let's put this distance into perspective with a thought experiment that will illustrate just how vast the cosmic ocean truly is. If we shrunk the distance between Earth and our Sun 93 million miles down to just 1 inch, Proxima Centauri would still be over 4.3 miles away. In this scaled model, our entire solar system, including distant Neptune, would fit within about 4 feet. The gap between us and our nearest stellar neighbor dwarfs everything we know. Here's the crushing reality: humanity's fastest spacecraft, the Parker Solar Probe, can reach speeds of about 430,000 miles per hour when diving close to the Sun. Impressive. Absolutely. Sufficient. Not even remotely. At that velocity, reaching Proxima Centauri would still require over 6,700 years. That's longer than all of recorded human history. The Voyager 1 probe, launched when disco was still popular, has been traveling for nearly 5 decades. It's now in interstellar space, having crossed the boundary where the Sun's influence gives way to the vast expanse between stars. Yet despite this incredible achievement, Voyager has only covered about 0.00% of the distance to Proxima Centauri. If Voyager were aimed directly at our target, which it isn't, our distant descendants 76,000 years from now might witness its arrival, assuming the probe systems could somehow survive that long. This is the tyranny of distance in space. Earth's entire orbital speed around the Sun is only 67,000 miles per hour. Even if we could somehow harness that, we'd still be looking at tens of thousands of years of travel time. The universe, it seems, doesn't care about human ambition or timelines. Chemical propulsion, the workhorse that has powered every human spaceflight from Sputnik to the International Space Station, hits a fundamental brick wall when we contemplate interstellar travel. The physics are merciless and unforgiving. Here's the mathematical nightmare. To accelerate a spacecraft to just 1% of light speed using conventional chemical rockets, you would need a fuel-to-payload mass ratio that's not just impractical, it's physically absurd. We're talking about 10-14 kilograms of fuel for every single kilogram of spacecraft. To put that in perspective, that's equivalent to the mass of a medium-sized asteroid, just to move a payload the weight of a laptop computer. Even if we could somehow gather that much fuel, there's another problem: the rocket equation. As you carry more fuel, you need more fuel to carry that fuel, which requires even more fuel in an exponential spiral of diminishing returns. The numbers quickly spiral into impossibility. Chemical rockets work on a beautifully simple principle. Burning fuel creates hot, expanding gases that shoot out one end, pushing the rocket the other way. But the energy density of chemical bonds, the amount of energy released when chemicals react, is fundamentally limited by the atomic structure of matter itself. The best chemical propellants, like liquid hydrogen and liquid oxygen, can only provide exhaust velocities of around 4.5 kilometers per second. That's the ceiling imposed by chemistry and thermodynamics. For interstellar travel, we're not just hitting the limits of our current engineering, we're hitting the limits of chemistry itself. This forces us into uncomfortable but necessary territory. We must abandon chemical propulsion entirely and embrace technologies that seemed like pure science fiction just decades ago. Nuclear propulsion sounds like the obvious next step. After all, nuclear reactions release millions of times more energy than chemical reactions. Surely that's our ticket to the stars, right? The reality is far more nuanced and, frankly, disappointing for those hoping for near-term interstellar travel. Let's examine the contenders. Engines, which have successfully propelled spacecraft like Dawn and Hayabusa, use electric fields to accelerate ions to tremendous speeds. They're incredibly fuel efficient, offering specific impulses 10 times better than chemical rockets. But they produce thrust measured in fractions of a newton, about the weight of a few sheets of paper pressing down on your hand. Building up to interstellar velocities would take centuries of continuous acceleration, and you'd still be looking at 4,000-year journey times to Proxima Centauri. Nuclear thermal rockets, which use fission reactors to superheat propellant before expelling it, can achieve exhaust velocities of about 9 kilometers per second, double that of chemical rockets. NASA and the Soviet Union both developed and tested these designs during the Cold War. The Nerva program in the 1960s successfully demonstrated the concept. Yet even this doubling of performance barely makes a dent in the interstellar distance problem. Then there's VASIMR, the variable specific impulse magnetoplasma rocket developed by former astronaut Franklin Chang Diaz. This elegant system uses radio waves to ionize and superheat plasma before magnetic fields channel it out the back at blistering speeds. On paper, it could slash Mars mission times from months to weeks. In practice, for a Proxima Centauri mission, we're still looking at over 2,000 years. The uncomfortable truth is that even nuclear propulsion, with all its promise, only shifts us from absolutely impossible to still effectively impossible for interstellar travel within human timescales. We need something far more radical. Now, we enter territory that sounds utterly insane until you examine the physics, propelling a spacecraft by detonating nuclear bombs behind it. This is Project Orion, and despite how absurd it sounds, it was seriously studied by brilliant physicists in the 1950s and 60s, including Freeman, Dyson. The concept is audaciously simple. You build a massive spacecraft with a thick pusher plate mounted on gigantic shock absorbers. Then you eject nuclear devices behind the spacecraft, detonate them, and let the expanding plasma from the explosion slam into the pusher plate. The shock absorbers smooth out the instantaneous impulse, and your spacecraft accelerates. Repeat this process thousands of times, and you've got yourself an interstellar ship. The physics actually work. Nuclear explosions release staggering amounts of energy in a tiny fraction of a second. By carefully shaping the explosive device using an ablative medium that channels the blast preferentially in one direction, you can achieve remarkably efficient momentum transfer. Calculations suggest an Orion-type spacecraft could reach velocities of 3-5 the speed of light, bringing Proxima Centauri within reach in perhaps 100 to 150 years. But here's where reality crashes the party. You'd need somewhere between 300,000 to 800,000 nuclear devices for a complete mission profile: acceleration, mid-course corrections, and deceleration. The spacecraft would need to be absolutely colossal, potentially 400,000 tons, with a pusher plate 100 meters in diameter. The engineering challenges are staggering, designing shock absorbers that can handle repeated nuclear detonations, protecting the crew and sensitive equipment from radiation and electromagnetic pulses, and ensuring that one malfunction doesn't doom the entire mission. There's also the small matter of international treaties. The Partial Test Ban Treaty of 1963 prohibited nuclear explosions in space. While Orion is technically feasible, the political, environmental, and regulatory hurdles make it a non-starter with current technology and geopolitical frameworks. It remains a brilliant idea, locked in the archive of maybe someday, but not today. What if, instead of carrying fuel, we left it behind entirely? This is the elegant promise of light sails, also called solar sails or photonic sail spacecraft, pushed not by chemical or nuclear reactions, but by the gentle pressure of light itself. Yes, light has momentum. Photons, despite having no mass, carry momentum proportional to their energy. When photons strike a reflective surface and bounce off, they transfer momentum to that surface, creating thrust. The effect is minuscule. Sunlight at Earth's distance produces pressure of only about 9 microtons per square meter, roughly equivalent to the weight of a grain of sand. But here's the beautiful part. It's continuous and requires no fuel whatsoever. Japan's Icaros probe demonstrated this concept in 2010, becoming the first spacecraft to successfully use solar sailing in deep space. The craft deployed a 20-meter diagonal sail and successfully demonstrated acceleration from solar pressure alone. Since then, missions like LightSail 2 have proven the concept works for Earth orbit applications. For interstellar travel, we'd scale this up dramatically. Imagine a sail hundreds of meters across, constructed from material just nanometers thick, essentially a giant mirror made of advanced materials like aluminum-coated mylar or even graphene. The closer you deploy this near the sun, the more intense the radiation pressure, and the greater your acceleration. But the numbers remain stubborn. Even with the perfect sail position optimally near the sun, acceleration is measured in millimeters per second squared. You'd build up speed gradually over years, but conventional solar sails would still require 1,000 to 2,000 years to reach Proxima Centauri. You've eliminated the fuel problem, but haven't solved the time problem. This is where human ingenuity gets creative. If natural sunlight isn't powerful enough, what if we brought our own light source? And our breakthrough, Starshot, arguably the most realistic and well-funded plan humanity has ever devised for interstellar travel. Announced in 2016 with backing from Russian billionaire Yuri Milner, Facebook's Mark Zuckerberg, and the late Stephen Hawking, this project represents a paradigm shift in how we think about reaching other star systems. The concept elegantly sidesteps many problems that plague other approaches. Instead of one large spacecraft, send thousands of tiny probes. Instead of relying on sunlight, use a massive ground-based laser array. Instead of trying to decelerate and orbit, conduct a high-speed flyby and beam data back home. Each decision trades complexity for practicality. The spacecraft themselves, called starships, would be revolutionary. Imagine a probe no larger than a postage stamp, weighing just a few grams, yet packed with cameras, power systems, navigation, and communications equipment. This is only possible because of Moore's law and the miniaturization revolution in electronics. These chips would be attached to ultra-light sails just meters across, made from advanced metamaterials capable of reflecting laser light with near-perfect efficiency. The ground-based laser array is where the engineering becomes truly audacious. We're talking about a phased array of thousands of lasers with a combined power output of 50-70 gigawatts, roughly equivalent to the entire generating capacity of a large nation's power grid focused on a single sail. These lasers would fire in perfect synchronization for about 10 minutes, accelerating the starships to 20% of light speed. or about 60,000 kilometers per second. At that velocity, the physics become almost surreal. The probe would cross the distance from Earth to the Moon in just 6 seconds. It would zip from New York to London in about 1/10 of a second. Proxima Centauri, our unreachable neighbor, would be just 20 years away. The mission profile is elegantly simple, yet fraught with engineering challenges. After acceleration, each starship would coast through interstellar space for 2 decades. During this time, navigation becomes critical. Any tiny deviation compounds over light years of travel. The probes would need to make micro-corrections using their limited onboard power. The flyby itself would be breathtakingly brief. At 20% light speed, the probes would tear through the Proxima Centauri system in just hours. Every sensor would need to work flawlessly in that narrow window. Cameras would snap high-resolution images of Proxima b. Spectrometers would analyze its atmosphere for biosignatures, oxygen, methane, or other potential signs of life. Magnetometers would measure the star's magnetic field and stellar wind. All of this data would be recorded and then transmitted back to Earth using laser communication systems. And here's the beautiful, patient part. 4 years after the flyby, the first signals would reach Earth. Traveling at light speed, those precious photons carrying humanity's first close-up data of another star system would be received by massive radio telescopes, perhaps descendants of today's facilities, perhaps entirely new arrays built specifically for this purpose. The challenges are sobering, but not insurmountable. Interstellar dust particles, though sparse, become deadly projectiles at 20% light speed. A collision with a grain of sand would vaporize the probe instantly. The solution? Send thousands of probes. Statistical survival replaces individual invulnerability. Keeping the laser accurately focused on a sail accelerating to 60,000 kilometers per second requires adaptive optics beyond anything currently deployed. The system must compensate for atmospheric turbulence, maintain perfect phase coherence across thousands of individual lasers, and track a target growing smaller and more distant by the second. Yet despite these challenges, the project has attracted serious scientific and engineering attention. Unlike previous interstellar concepts that remain pure theory, Starshot has actual funding, working groups, and research programs actively developing the necessary technologies. The laser systems, metamaterials, and spacecraft miniaturization are all progressing in parallel. Could we see this launched in our lifetime? Possibly. The timeline estimates suggest that with sustained funding and no major technical showstoppers, a demonstration mission could be ready within 20 to 30 years. That means someone watching this video right now could live to see humanity's first interstellar probe launched and possibly even receive the first data from another star system. Let's engage in some informed speculation about what awaits us at Proxima Centauri. Proxima b orbits its star every 11.2 days at a distance of just 7.5 million kilometers, 25 times closer than Earth orbits the Sun. But remember, Proxima Centauri is a red dwarf, emitting only about 0.17% of the Sun's luminosity. At that close distance, Proxima b receives roughly equivalent energy to what Earth receives, placing it squarely in the habitable zone. But habitability is complicated. Red dwarfs are notorious for stellar flares, violent eruptions that can temporarily increase the star's brightness by factors of 10 or more. These flares blast out intense ultraviolet and X-ray radiation, along with charged particles that could strip away a planet's atmosphere over millions of years. For Proxima b to retain an atmosphere thick enough to support liquid water, and possibly life, it would need either a strong magnetic field to deflect this onslaught, or such a thick atmosphere that the losses could be replenished through volcanic outgassing. There's another consideration: tidal locking. At such close orbital distance, Proxima b is almost certainly tidally locked, meaning one hemisphere permanently faces the star while the other freezes in eternal darkness. This creates extreme temperature differentials. However, if the planet has a sufficiently thick atmosphere, heat circulation could moderate these extremes, potentially creating a twilight zone region between the day and night sides where conditions might be temperate. What would that world look like through the cameras of a Starshot probe? If Proxima b has retained its atmosphere, we might see cloud patterns, possibly concentrated in the perpetual day side, where the star's energy drives convection. The night side might feature glacial ice sheets kilometers thick. The terminator, the boundary between day and night, could host the most habitable regions, where temperatures moderate and liquid water could exist. If we're extraordinarily fortunate, spectroscopic analysis might reveal biosignatures, molecular oxygen produced by photosynthesis, methane, that could indicate biological processes, or other chemical disequilibria that are hard to explain through geology alone. Finding life, even microbial life, on the closest exoplanet to Earth would be the most profound scientific discovery in human history. It would answer the ancient question, are we alone? And the answer would be a resounding no. But even if Proxima b proves barren, a radiation-scorched rock with no atmosphere, the scientific value would be immense. We'd learn about planetary formation around red dwarfs, the most common type of star in the galaxy. We'd understand atmospheric retention and loss mechanisms. We'd gather data about stellar planetary interactions that would inform our search for life throughout the cosmos. And let's not forget, Proxima Centauri might host other planets we haven't yet detected. Each one could teach us something new, something unexpected, something that challenges our understanding of how planetary systems form and evolve. Carl Sagan once observed that a civilization that reaches the stars will necessarily have matured beyond its destructive adolescence. The very act of planning for interstellar travel forces us to think in timeframes beyond quarterly earnings reports or election cycles. It demands we consider humanity not as nations or ideologies, but as a species with a shared destiny. The practical arguments for interstellar exploration are compelling. Earth, for all its beauty and resilience, is a single point of failure for our species. Asteroid impacts, supervolcano eruptions, nuclear war, climate catastrophe, or emergent pandemics, any number of scenarios could severely damage or end human civilization if we remain confined to one planet. Establishing even a secondary foothold elsewhere, whether in our solar system or around another star, dramatically improves humanity's odds of long-term survival. But there's something deeper than mere survival at stake. Humans are explorers by nature. Our ancestors left Africa and populated every corner of Earth, crossing seemingly impossible barriers, vast oceans, frozen tundras, scorching deserts, driven by curiosity and hope. That same drive propelled us to the moon, and has sent our robotic ambassadors to every planet in our solar system. The stars represent the ultimate frontier, the final unknown. A species that stops exploring, that becomes content with its current boundaries, is a species that has stopped growing. The challenges of interstellar travel requiring cooperation across nations, advances in multiple fields of science and engineering, and commitment spanning generations. These challenges force us to become better than we are. Consider what reaching Proxima Centauri would mean. It would demonstrate that no destination in the universe is beyond our eventual reach. It would prove that with sufficient determination and ingenuity, humanity can overcome any obstacle. The technological spin-offs alone would transform life on Earth. Just as the Apollo program gave us everything from integrated circuits to freeze-dried food. More importantly, it would fundamentally shift how we view ourselves. We would no longer be humans of Earth, but humans of the cosmos. That perspective, seeing our planet as one world among countless others, has the power to unite us in ways that political movements or religious doctrines cannot. The question isn't whether we can afford to go to the stars. The question is whether we can afford not to. Every great human achievement once seemed impossible until someone decided to make it possible. The pyramids, the cathedrals, the Great Wall, the internet, all were built by people who couldn't see the completion of their work, but believed the effort mattered. Reaching Proxima Centauri will require that same faith that the journey matters as much as the destination, that the struggle to achieve the seemingly impossible refines and elevates our species. The first humans to see data from Proxima b might not be born yet, but we, here and now, can lay the foundations. We can fund the research, develop the technologies, and inspire the next generation to carry the torch forward. The universe is vast, ancient, and indifferent to human ambition. But within that vast indifference lies infinite possibility. Proxima Centauri is just the beginning. Beyond it lie billions of stars, each potentially hosting worlds stranger and more wonderful than we can imagine. Some might harbor life, perhaps even civilizations who've already solved the problems we're grappling with now. The journey to the stars is humanity's ultimate test, a challenge that will demand the best of our science, the depth of our courage, and the breadth of our vision. It's a challenge we must accept, not because it's easy or profitable or certain to succeed, but because it's worthy of who we aspire to be. As we stand on the threshold of becoming an interstellar species, we face a choice. We can remain bound to our cradle, watching the stars from afar, or we can take those first tentative steps into the cosmic ocean. The light from Proxima Centauri has been traveling for over 4 years to reach your eyes tonight. By the time you see it, that light is ancient history, a glimpse of the past. But the future? The future is ours to write. If this journey to Proxima Centauri sparked your imagination, if it made you look at the night sky differently, then hit that like button. It helps us reach more curious minds like yours. Share this video with anyone who's ever wondered what lies beyond our pale blue dot. And subscribe to BrightBoundX, because we're just getting started. From black holes to quantum mechanics, from artificial intelligence to the search for extraterrestrial life, we're exploring the ideas that will define humanity's future. The comments are open. Tell us, if you could send one question to Proxima Centauri and get an answer back in your lifetime, what would you ask? Let's dream together. Until next time, keep looking up. The universe is calling, and BrightBoundX will be here to explore it with you. Subscribe to BrightBoundX. The future is closer than you think.